Hi everyone, my name is Daniel Stig-Franse, and I'm here to talk about fast and robust quantum state tomography from few basis measurements. And this is joint work with the great Vanilla Brandão and Richard Kuhn. You can find the paper this talk is about in the archive. It has the same title as this talk, and you find the archive number below. Okay, so what is this talk about? So the main problem we're going to address in this talk is that of tomography of quantum states of low rank. Okay, so what is the framework? We are given access to copies of some quantum state sigma. So we know it's in dimension D. So D is the dimension, not the number of qubits. And we have the promise that it is of approximate low rank. So say it is close to a pure state. And we are allowed to perform measurements on individual copies of sigma. So we get a copy of sigma and then we measure it. So in particular, we are not allowed to say store 20 copies of sigma in a quantum memory and then measure them all collectively, because being allowed to do this actually changes the parameters of this problem. And our goal is to obtain a classical description of a state sigma prime that is epsilon close in trace distance to sigma up to some small probability of failure. So by classical description, I just mean that, like I have a quantum device that I press a button, it produces me a copy of sigma that I can measure, and then I want to store a representation of the state sigma prime here on my laptop that is close to the target state. And what are the relevant resources when talking about this problem? First, of course, the number of copies of the state sigma required. So how many times you have to press the button and get a copy of sigma and measure it. This is the sample complexity. But it is also quite important to optimize the number of measurement settings. So from an experimental point of view, it is also quite annoying to change the observable or we are actually measuring, or the basis we are measuring. So it is important to optimize for that. We also want to make the classical post-processing. So after we acquire the data, how long does it take to actually get a classical description of the state to be as fast as possible. And you also want to minimize the classical memory required for this post-processing, because as I'll discuss in a bit more detail later, this is actually one of the bottlenecks in many state-of-the-art proposals to solve this problem. And there's, of course, some additional things that are quite important for any sort of protocol for quantum state tomography. First of all, we want to be robust with respect to spam. By this, I mean state preparation and measurement error. I don't mean it in the randomized benchmarking sense of the word that we can get rid of all errors in the implementation. I just mean that we want to make sure that the protocol also works under realistic noise, because it will always be present. And it might be also desirable for the algorithm to be online. That is, while we're still acquiring the data, we can already start doing the post-processing. This could significantly speed up the time required, from measuring to actually obtaining a classical description. And we want the simple measurement, the measurements we have to perform to be as simple as possible from an experimental point of view. So let's discuss how well our algorithm does. So this is summarized by this table. So on the first row, you see the lower bounds known in the literature. So R here is the approximate, is the rank of the underlying quantum state. So we know that by work by Wolf that we need to recover a state of rank R, we need at least R measurement settings. By work from Harrow and we know that we need at least D to the R squared epsilon to the -2 state copies. And of course, we have to read in this data. This also gives us a lower bound on the runtime. And of course, just to store a state or an arbitrary state of rank R, we need to store D times R parameters. And importantly, you see that our algorithm essentially matches the lower bounds for the basis setting, state copies, and memory up to some dependency on the error. So again, epsilon is how close you want to be, and trace distance, right? And this is the first algorithm, as far as we know, to do this for all parameters simultaneously. So you do have other proposals that, for instance, like compressed sensing methods that can get away with R basis settings to recover a rank R state. However, it is unknown what the number of state copies is for you to get a recovery up to error epsilon, and the runtime and the memory you need are significantly higher than the lower bound tells you. And the same for projected least least squares, which is another state-of-the-art method where the number of basis settings is actually exponentially higher than what the lower bound says it has to be. While in our case, we, again, as long as epsilon is not too large, match lower bounds. So, and importantly, our algorithm is also robuster than all of the above. So for these algorithms I mentioned before, like compressed sensing and projected least square methods, it is difficult to prove that they are robust. And as I'll show you later, in practice, they're also, at least compressed sensing, is not as robust as our method. It should also be said that our method can also be implemented on a quantum computer, and we obtain a quantum speedup. Then we can bring the runtime from d squared to d to the 1.5. And again, as far as we know, this is the first rigorous tomography result that can do the post-processing in quadratic time. And it, of course, in implementing the algorithm on a quantum computer will also give you as the output a classical description of the state. And it must be said as well that all of the results above only hold up to a constant probability of success, and we are suppressing polylog terms in D. I should also mention that, to the best of my knowledge, this is the first algorithm that can also rigorously analyze some other measurement setups. Say, instead of having 4 design measurements, we have random Clifford measurements, which are 3 designs but not 4 designs. Then we can show that the algorithm still retains its nice features up to a higher dependency on the rank. Okay, so what is the building? Well, there are 2 building blocks of our algorithm. So other algorithms to solve this low rank tomography problem, they try to solve a linear inversion problem. So they gather all the data and then they solve a linear inversion problem. But our algorithm is iterative. In some sense, it is close to some other proposals in the literature, like self-guided tomography, and it is based on mirror descent, which is an optimization technique with the von Neumann entropy as potential. And the update rule we use to show the convergence of our algorithm is the same behind some recent quantum speedups for semi-definite programs. So this is the update rule I mentioned before. As I said, we are not the first ones to, of course, prove this convergence, and it has been used for semi-definite quantum speedups or semi-definite programs, or also even for tomography. But we are the first to use it to give like finite time, finite sample complexity guarantees in this basis measurement setting. And it essentially tells you that if you let S be the relative entropy between your state at some iteration t and the target state, which in this case is rho, then as long as you have some projection that allows you to distinguish your current state, your current guess of the state from some target state, then you're gonna make the relative entropy between the the target state and your current state will strictly decrease. Okay, so this update rule allows us to reduce doing tomography to actually distinguishing quantum states. And we have the promise that as long as we can distinguish the target state from quantum from our current guess, we're going to make progress in relative entropy. And we can then, for all sorts of measurement setups, just take some literature on distinguishability of quantum states and lift it to result on tomography. So for instance, for random unitaries, it is known that this follows from results by Leon et al., that that on average, a random unitary allows you to distinguish two quantum states up to their Hilbert-Schmidt distance. So as long as the Hilbert-Schmidt distance between two quantum states is not too small, measuring a random basis will allow you to distinguish them. And also the converse is also true, which is what this inequality tells us, namely that if you measure a few bases and the two states are indistinguishable, then they're likely to be close in Frobenius distance. And then what we can then use, I mean, in the end, we're interested in recoveries and trace distance, not Frobenius distance, is the fact that for states of small rank, so if either rho or sigma is of small rank, then the Frobenius distance and the trace distance are essentially the same up to a factor which grows like the square root of the rank of one of those states involved. And we also generalize these sorts of results for states that have a small Renyi entropy, which can be seen as a as a continuous relaxation of the rank. And it should also be said that to show a result like this, it suffices to look at the first 4 moments. So the same results holds for 4 designs. So here we just have an illustration of how the algorithm works for a qubit. You start from the maximally mixed state, which is the state here in the middle of the Bloch sphere. You measure some basis. You compare the current iterate with the state you're performing tomography on. You compare the statistics. You use this data to get an update, and so on. So you update your state, you again measure basis, compare statistics, and so on. And if you do this a couple of times, you're guaranteed to converge to the true state. And as I mentioned before, the algorithm is also practical. So here we see the performance of the algorithm for random states on 15 random global basis measurements. So we are allowed to measure 15 random bases. And the blue line corresponds to compressed sensing. The orange one is our algorithm, which we call Hamiltonian updates. And here we also added amplitude damping to the measurement outcomes with probability 0.005. And we set our recovery to be of order 0.01, that is 10 to the minus 2. And you can see clearly that the quality of the recovery for compressed sensing methods decreases much faster the number of qubits than our methods. Moreover, due to memory constraints, we can only do up to 7 qubits, at least on my laptop, with compressed sensing methods, while our method can easily handle much more, say 10 qubits. So we see that also these memory constraints are significant in practice as well, and that this method is actually competitive against state-of-the-art methods. So we do much more in the paper, actually. There are also some things which might be of independent interest, like the fact that we show how to efficiently diagonalize quantum Gibbs states of low rank, and some other nice results you have to prove along the way to get our algorithm. We also discuss the trade-off between the locality of the measurements and the sample complexity. So I'll refer you to our paper for more, and thank you for your attention.